which are full, and these are empty here. So this is the last value which is full. It goes to this place. Now, if the array is completely full, obviously you cannot insert. It's already full. Okay, so if that's full, you cannot insert. There is no space. Right? So we are talking about the situation where insertion is possible. Okay, and insertion is possible only if there is at least one empty cell in the array. So we said that insertion is expensive. Okay, the only way to deal with it, actually, in this case, is to create a larger array, like double size or something, and so we copy the elements first, and then we do the insertion as we have seen in the examples here. We start doing shifting, or maybe be more clever and do the shifting as we are copying. It depends on the implementation. Okay, but this is more expensive. Obviously, this is more expensive than this because it requires copying. Okay. But if we go back to the example here, okay, insertion can be very inefficient in the array because it causes a lot of shifted element. Actually, an array of size n, if it has, for example, n minus 1 cells which are full and one empty cell, then we are going to have n minus 1. In the worst case, we can have n minus 1 shift operations. If the array is completely full, like in this case, we are going to have n shift operations. So in the worst case, what is the complexity of the shift operation? Of the insertion? I mean, try to think of it as if you are implementing a program. So you have insert some x into some array, and you want to program this insert operation. Okay. So a has size n, x is just one value, the array has size n, and now you want to know the complexity of this operation. And when we talk about complexity, we are talking about how many runtime steps does the algorithm need in order to process this input. So this is one value, and this is a value which is n. Okay, so the algorithm here, is it going to be big of 1? Is it going to be big of log n? Is it going to be big of n? Is it going to be big of n squared? The number of steps in the worst case. What is the relationship between the number of steps and the size of the input? So what is the relationship between the number of steps and the size of the input for the insertion operation, in your opinion? Yeah, assume the general case where the input is n. Okay, you have an array. Your input is an array of size n. If you cannot work with n, try any size. Try 100. So you have an array with 100. Now think about a worst case here. Think about a worst case situation. What is the maximum number of shift operations you can perform if you need to insert an element in an array of size 100? Okay. So, for example, the array has 99 elements, right? Okay. So, how many operations are you going to need here? How many shift operations?
99.
Right. Now, if it was a million, you are going to need 6 nines, right? So, what is the relationship between the number of steps and the input here?
Minus 1.
And n minus 1 is big O of what? We, no. Okay.
What is that?
Wow. Okay. We said that if we have a polynomial, okay, if we have a polynomial like n squared plus n plus 1, we said in order to find complexity, we remove all these elements and we remove the constant factor, and this becomes big O of n squared. Now you said you have n minus 1 steps, and so this is a polynomial. Just remove that and you will get big O of n. Okay. Now, this is insertion. Now, what about deletion? We have an array. I hear a lot of people coughing. Is it because of the quiz? 10, 5, 6, 7, 8. Now, we want to delete an element. We want to delete element 6. So we have numbers. I cannot think of numbers anyway. 20. Let's say we have an array full of numbers and I want to delete 6. Now what happens when I delete 6 usually is we cannot just delete an element from an array and leave it like that. Okay? We cannot just delete 6 and leave this cell empty. When we delete something from the array, we need to restore its property of being contiguous. Okay, so this is our array of data. It's full. If we make this empty, we need to shift these elements this side. We need again to make the array look contiguous. Okay, so if we delete an element, we cannot just leave the cell empty, because there are lots of things which depend on, like when we traverse an array from the beginning to the end, what happens if we... Lots of things which depend on, like when we traverse an array from the beginning to the end, what happens if we encounter a cell which is empty? I mean, what does it mean? There is no such a thing as empty to start with. Empty means it does not contain 6. It contains garbage. Okay? So delete, when we say delete, this is not a blackboard where we are going to delete this like that. This is a register in main memory. Okay? That's a place in main memory. So there is no such a thing as delete. No? We are not going to just make it like that. Are we going to make it 0? Are we going to make it -1? You know? You don't know. Okay? Depending on the algorithm implementation. Maybe if we want to find the maximum of these numbers, and they are all negative, and after deleting we make this 0, and then this is returned as the maximum. This is wrong. Okay, so delete, there is no such a thing as delete, and that's why deleting here means that we have to shift everything back, right? So deleting an element, in this case we will have 10, 8, 5, and we have deleted 6, so 7 now. So everything now starts shifting. So if we delete the first element in an array of size 100, how many shifts do we need? Array of size 100, and we delete the first element, how many shift operations do we need? Right. So the complexity of the delete operation is big O of n. Yes. It's linear, just similar to the other. In the infinity, if n is a billion, it's going to be billion minus 1 in the worst case. Obviously, I can also delete the last element. If I delete the last element in the array, how many shift operations do I need? 0. However, we said that in asymptotic complexity, we consider the worst case. Okay? So we are not going to consider the case where we delete the last element. We are going to think in the worst situation. The worst situation happens when we delete the first element, and this is what gives us the worst case. So the worst case in this case is when we delete the first element, and it's big O of n. So the complexity of the delete operation of an array is big O of n. Now is that clear?
Yes.
So the shift operation for when we insert, this is called shift to the right, and when we delete, we are shifting to the left, right? I mean, correct? Inserting, we are shifting to the right because we need to make room towards the end, because the end is potentially empty, because we know that there cannot be any empty cells at the left hand side, because it's a contiguous data structure. And when we delete from the array, we are going to shift again to the left, unless of course the element that we are deleting is the very last element. So arrays and records are nice, contiguous in my memory, constant time. They have constant time access, constant time access, and when we try to delete or when we try to insert, they take a linear time, big O of n. Right? Now, what is traversal in an array? We want to traverse elements of an array. What is the complexity of that operation? Traverse elements of an array. What is the complexity of that operation? We want to traverse. You know traversal? The word traversal. To traverse. You're kidding me. Traverse. You don't know the word? Right. يعبر. Okay, traverse means يعبر. So we want to traverse the array from the very first cell to the last cell. What is the complexity of this operation? Come on, you should give me the answer in 10 seconds. This is very easy. Yes, big O of n if we assume the array has size n. So array traversal is big O of n if the array has size n. So you have an array of 100 elements and you want to traverse it, which means visiting each element in the array once. So visit the first one, visit the second one, the third, etc. This is what you do when you try to compute the maximum. You visit everything. If you want to compute the sum, you traverse everything, visit everything. When you want to compute the average, you visit everything, you traverse everything, and all these operations, they take big O of n. Okay, you traverse all array cells, and this takes you big O of n complexity if the array has size n. Right, now enough talking about arrays. We know what's good about them, we know what's not so good about them. Now we are going to talk about linked lists. Okay, so we said arrays, far from asymptotic complexity, arrays are static arrays. We need to know the size of the data before we can use them. Now, if we don't know, we might use something like a dynamic array. The problem with dynamic arrays is that they are not available in all programming languages, and if we try to implement them, we might not do it very efficiently. Now, linked lists are a better compromise. So now we are going to talk about linked lists. Okay, what is a linked list? That is a linked list. Makes perfect sense? Okay, so let's spend some time talking about what a linked list. Let's see if I have further. No, I have nothing. Okay. So let's say that we have asked the user to input some numbers. Okay. We want to write a program that is going to ask the user to input some numbers, and we are going to give the sum of these numbers. We are not telling the user input 10 numbers or 5 numbers. We are going to ask the user to input some numbers. Okay? So we cannot use an array. We are going to use a linked list. Now, how does it work? Now, assume so we cannot use an array. We are going to use a linked list. Now, how does it work? Now, assume the user has input the numbers 7, 5, 1, 3, 12. Okay, so the user has input 5 numbers, but we don't know they are 5. Now, we are going to use a linked list. So, how does it work? The user is going to tell us my first number is 7. So what we do is we take this number 7 like this and put it inside the record. Then I will explain more later on, okay? And then the user is going to input number 5. So the user is saying my next number is 5. What we do is we create a record for 5 and create a link between 7 and 5. And then the user is going to say my next number is 1. So we create a record for 1 and we create a link between these. And then the user inputs 3. We do similarly. And finally the user is going to input 12. We create a record for 12 and link it. This is called a linked list. It's a list and it is linked. Okay, there are these links. We need these links, otherwise, because we don't want the data to be lost. When we define an array is a piece of main memory, so we know all these elements here, they belong to the same array. But these elements, we need to link them together so that we know what's going on. So we can go from this to this element, etc. So this is called a linked list. Now, let's do it one more time with a little bit more detail. The user has decided to input 7, 5, 1. Three, 12. Okay? So the first what we are going to get is 7. We said we are going to create a record for it. Now what does that record mean? The record is something like that. We are going to use this representation. We are going to put the data inside this field, and here we are going to define something called pointer. A pointer basically is something that points to the next record. If you remember, the previous one was something like that. 7 points to 5, which points to 1, which points to 3, which points to 12, right? So everything is pointing to something else. Now, the first data that the user is going to give us is 7. So we create a record. It has the value 7, and it has a pointer. Now, at the beginning, the pointer doesn't point to anything. We don't have any other record. And that's why we use this symbol. It's like Earth. In electrical signals, this is like Earth, okay? So we use this. So we use this symbol. So after the user has input the first number, we create a record like that. Then the user is going to input 5. So we do something similar. 5. It doesn't point to anything. However, now we need 7 to start pointing to 5. So this is going now to point to 5, which is what I have drawn here as just an arrow. Now 3, what I have drawn here as just an arrow. Now 3 is another record. And now this one is going to point to 3. And then what? I made a mistake. That should have been 1. 3. And this points to 3, and this points 3 points to nothing. And finally 12. It points to nothing, and now 3 points to 12. Okay, now this is what we call a linked list. So each element becomes a record of one part. Oops. A record of one part, which is the element itself, okay, and another part, which is the pointer, which points to the next record. So this is a linked list. Now, we will go even further in detail. Now, we need to know what is a pointer. What is that arrow here? Okay. What really happens is, if we look at it in main memory, so this is main memory. We have addresses here. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then the user is going to input the number 7. So we said we are going to create a record 7 like that, right? Now what does that mean? Do I have colors? No, I don't. So what does that mean is we are going to choose a location in main memory. At the beginning it doesn't really matter. So let's say we put 7 here. And then this null pointer is going to be nothing. It's going, for example, to be a specific value. For example, let's say it's -1. We are going to use a value specific for this pointer. We call it null. It's the null pointer. It points to nothing. So this record now becomes this place in main memory. Now we insert another number. We said, I think we said 5. So we are going to, let's say, put it 5 here. And it has a null record here. So this is this record. And then we said that 7 should have a pointer. This null pointer now points to 5, right? Now what does that mean? This now should change. Now 5 is at address 7. So this -1 now becomes 7. Okay, this 7 is not that 7. It's just by coincidence, okay? It's just coincidence. So now, this is our linked list. Now let's put 3. And let's put it here with -1. And now we need to link 5 to 3. So what happens in main memory? Now we need to link 5 to 3. So what happens in main memory? We have created a link from 5 to 3. So what happens in main memory? So 5 had a null pointer, which is -1. Now it's pointing to 3. So what happens to this -1? Come on. it becomes 5. Oh my god, another coincidence. Okay. Okay, that's just another coincidence. Okay, let's do it again, because I know you will get confused. Yeah, you know you get confused, don't you? So, first things first. We put 7 like that. Actually, it's my mistake. Let me put these addresses as 100, 101, 102, 3, 4, 105, 6, 7, 8, 9, 10, 111, 112, 113, 114, 115, 116. Right. Then we put 7 somewhere. Let's put it somewhere which is not into it. Here. 7 and minus 1 for the null pointer. So this is 7. And then we have 5. Let's say it goes here. 5 and minus 1. And then we need to link 7 with 5. So what happens now? What happens? So the minus 1 where? In 105 becomes... No, it becomes 111. It becomes the address of this number. Yeah, it's the address. It's the address of this number here. Okay? So this one becomes the address, so that we know where it is. And then 3 with the null pointer. Let's say we put it here. Minus 1. So this is 3. So what happens now? We said that we are going to delete this pointer, the null pointer, and make it point to 3. Okay. So the minus 1, which is at 112, is going to become... Okay, 108. I know I'm giving you a hard time reading my handwriting, but... Okay, 108. I know I'm giving you a hard time reading my handwriting, but... 108, okay? And so on and so forth. So, again, I mean, we went from this representation, okay, so that we know what's a linked list, to actually saying that linked lists are actually represented as records, and then finally representation in main memory. This should bring us to the slide, wherever it is. Here it is. So here we have, for example, 2 is pointing to 6. Where is 2? 2 is here. And this is the record of 2. And where is 6? 6 is here. So this is the address 1051, which is the address of 6. So this is the last thing that we have reached in our explanation. So this is what is a linked list. So we don't know initially the size of the different items, okay? Not the size, sorry, the number of different items. So we start putting them in. The inside main memory and linking them to get a linked list. Yeah.
We will use the address.
Say it again.
We want to retrieve any kind of data that we store it now.
Yeah.
So we will use the address as well, or
If we remove a record.
no? I mean, if I want to retrieve an entity.
Oh, no. No, the address is not. I mean, it depends. If your program is written as, let me just lower the volume. For example, when in terms of programming, what you will create records of data. So you will say, I have the following record. It has an integer x, and it has a pointer. And then you are going to create a record for number 3, for example, a record for number 2, etc. When you are going to retrieve the data, let's say the whole thing is one record, okay? So you will get record 3. It has both the integer 3. Okay, let's use 2 here as example. Okay. So let's say we have record 2. Record 2, it has the value, the integer value, which is, where is record 2 here? It's this one. It has the value 2, and it has the address 1051. So in terms of programming, these elements are always together. But in programming, you don't have an address, okay? You have just a pointer. Like in your class, for example, if you are using Java, what you will have, for example, is class, and you call it customer. And inside it, you will have different fields like gender, well, not gender really, purchase history, date of birth, well, not gender really, purchase history, date of birth, things like that. And you will have a pointer. Now, the pointer in Java is just a class. So you will say something, you call it pointer, and it is type customer. Okay, it basically, it links this customer, this record, to another record of the same type. Say it again.
What the benefits of using this address to store this data?
What is the benefit of using an address?
Yeah, for the when address.
Okay.
Can I answer?
Okay, go ahead.
Because the array, when we need to store array, we need to make space all the rooms of the array with each other. But this is a problem. When I am searching in the memory, the place have maybe million rooms to store array. But we in linked list, this is solution of a problem in array. I can store many rooms in memory, but not always in the same place. Maybe in any room, not each
Yeah, thank you very much. I mean, what you are saying is, if you have a big array of data, maybe you don't find space for it in main memory. But if it is a linked list, you can use all the little small slots here and over there in order to store all the data, right?
Yes, yes.
I said it in 10% of your time. Okay. But your answer is very clever. Okay, you got the answer right.
But I can say that in Arabic shorter.
Yeah, you wish. Okay. Okay, the time, I think the time is up, and I don't know if this was the answer to the question actually. Um, was the question about if the linked list, what is the benefit of a linked list, which is what we are going to see later on, or is why do we use addresses? If it is why do we use addresses, it's because when you program, this is what you write, but the computer is not going to understand this, and that's why it translates them into addresses like that. So this is why we have addresses. This is something that you are going to see inside the memory. You are never going to use addresses like that. Actually, you are going to program it like this. So that's why we have addresses. Now, if you were talking about why why do we use linked lists and why do we not use arrays, this is something like your colleague has said, and we are going to also discuss it more in more detail next session. Okay, so I think we're done, and yeah, thanks.